everyone. Today's topic is about quantizing large language model, and I'm Supriya Raman here presenting this for you. When we talk about quantization, it is an excellent technique to compress the large language model and it accelerated inference. Quickly taking you through the agenda which we have today, we will first explore through why we need quantization. How is the numerical representation? Basically, if you are representing anything into the machine, how it is internally represented inside the machine. And then we will talk about what exactly is quantization and what are the different type of quantization which is available to us. And finally, we will wind off with talking about some of the challenges which are present with the quantization. Talking very briefly about myself, I'm with 18 years of experience. I'm Supriya Raman here. I work as a senior VP data engineering at JP Morgan Chase. And in my current role, I'm responsible for defining and leading analytics solutions, which leverage data science, machine learning, and AI solutions. Basically, I'm directing end-to-end model development and deployment life cycles. And my key skills are mainly in NLP and generative AI. I'm very actively involved in the career mentoring and upskilling and coaching students, and also from even reputed in university. And I'm also working with some of the working professionals. In my current capacity, as a volunteer working for Google as a woman technical ambassador, and I'm IEEE woman entrepreneur organizing team member also. With that, let's start with the prerequisite of the topic today. The prerequisite, of course, because it is talking about quantification, we should have a basic knowledge of the neural network and some basic knowledge of the high school mathematics. But having said that, if you don't need this prerequisite, don't worry, because Harvard Business Reviews, it talks about learning is supposed to feel uncomfortable. So even if you don't meet this prerequisite, feel free to become uncomfortable and please join hands in order to explore this topic further, because I promise you that I will surely help you to scratch the ground. Before we start talking about quantification, let's talk about the rise of large language model. And the rise of large language model in recent years has been nothing short of remarkable. These are very powerful tools which help us to process and understand language. It enables us to achieve unpredictable level of accuracy and efficiency in wide range of NLP tasks. But how it is being, what is driving this rise? In simple terms, if we talk about, it is all about data, hardware, and software. And the availability of the large amount of annotated data had been critical in the development of these models. If you see the rise, of course, the hype of the generative, the large language model happened when the chat GPT came in 2022. But what I want to highlight in this slide is the rise actually started much before it in 2014 when we had GAN models. In fact, the basis of all the large language model are the transformer model or the encoder decoder model, and it started with 2017 when the paper of transformer came. The paper name was Attention is All You Need, which has been published by Google. And soon after, we had GPT model, GPT 1, 2, 3, and finally in 2023, we have GPT 4. This is all about the landscape of only the OpenAI models, but we will talk about there are huge amount of models in the market these days, and we will explore it in few minutes. Before we actually talk about why we need it or what is quantification, let's talk about what is the advantage of it. So when we say large language model, the word large is basically related to huge size. Huge size means huge memory occupation, and of course you need huge machines in order to process it, to compute it. If you use quantification along with large language model, you will reduce the memory consumptions, and therefore your model can run on smaller devices like your smartphone. Also, inference time. This is a very fancy term which has come up with the large language model. We will explore it further in upcoming slide. You will be able to reduce your inference time and thereby reducing your computation, which is directly related to your cost. So huge use saving if you use quantification along with large language models. This picture, and you might have seen many similar pictures in internet, it actually shows you many large language models which are available in the market. If you can see, we started with BERT, GPT-1, GPT-2, and finally we are at GPT-4 now. If you see, the initial models had parameters in millions. So BERT had 340 million, while GPT-1 had some million. And initially it started with billion, and then in between you can see bigger circles where we have billions of parameters. And finally, we are at models which are having parameter in trillions. Therefore, with each upcoming model, we have increasing number of parameters. So what constitute this model size? Why are these parameters too huge? It is not only the parameter, but there are other factors also. Basically, when we talk about model size, there are four major aspects of it. The first, of course, is about the model size, and there are million and billions of parameter storage, which we saw in the previous slide, and they are stored in VRAM. We also have activation. Activation are basically the temporary storage, and it is the data which passes from one layer of the neural network to the other. It is basically the product of your input and the weights. When we talk about batch size, the picture clearly shows it is the amount of intake which you can take in one go. That means it is number of samples which is used in one forward or backward pass through the neural network, and it has a direct impact on the accuracy and the computational efficiency of the training process. And finally, we have precision. When we talk about precision, it is basically what type of data type you are using in order to store each single parameter. So depending on what data type you choose, you will have different bit of representation. And the picture which shows the image cookies picture, right? You can see that if you choose lesser bits in order to represent your data, you will actually have you will actually lose the granularity, and the picture will not go as clear as it was. And of course, you will miss out accuracy when you're talking in terms of models. So altogether, we see that in model size, we have four different aspects which actually construct the model size. Also, when we have the numerical representation, quickly talking about numerical representation, this is something IEEE standards. Basically, if you talk about data, right, each single character or number is represented using bits, and we have either 0 and 1. Therefore, if you take an example of 3 bits, then the number of possible combinations which you can use with 3 bits is 2 to the power 3, which is 8. And therefore, you can represent the number from 0 to 8. If you talk about the major data types which are used in order to represent, we have int 8. When we say int 8, it is 8 bit of representation of integer, and it ranges from minus 127 to 127. Also, we have FP36, half precision value, 16 bit of storage, floating point. And also we have FP32, floating point, 32 bit of representation for full precision representation. Now, in the examples below, if you see, the same number has been represented using 16-bit and the 32-bit. If you take 16-bit or a 32-bit representation, in both the cases, the first bit is always used in order to store the sign. If you have a 0, it indicates positive. If you have a 1, it indicates a negative. If you have 16-bit of representation, then 5 of the following bits are used in order to represent the exponent part. While if you take a 32-bit of representation, you have following 8 bits in order to represent your exponent part. And the remaining part is always used in order to represent a decimal value. On the left part of the screen, you can see that the same number has been represented using 16-bit of representation and 32-bit of representation, but you have higher precision using 32-bit of representation, of course, because you are using much more bits in order to represent the same value. There are few terminologies which are related before we actually talk about quantization. We have GPU. In order to process these models, we need machines, and the machine which we use is CPU. But CPU cannot support such huge LLM models, and therefore we need GPU, which stands for graphical processing unit. We need VRAM, which is basically video random access memory. It is an accelerated compute, and it is used for the faster data transfer. Also, we will talk about LLM inference, and the whole game is to optimize this LLM inference, and that's why we need quantization. So when we talk about LLM inference, you take any LLM model. As soon as you provide an input, which is called a prompt, to finally when the LLM will give you the output, which is called a response. The time frame between when the prompt has been provided to finally when you get your response is called your inference time. And this is what you really want to optimize. While you are optimizing it, basically you are trying to optimize how much VRAM has been consumed, right? There are various formula which has been available, and one of the most common formula it talks about, which is highlighted in green there, it talks about number of parameters called precision divided by 8 into 1.2. 1.2, 20% of it has been saved for activation. This is one of the most common formula. We have multiple formulas for this. So example shows that if you take a minstrel model having 7 billion parameters, then you will need 16 GB of VRAM. And some assumptions having maximum sequence at 512, batch size of 8, and assuming that you're using only single GPU, you can always use multiple GPU at any point of time. So there are various VRAM calculator which is available, but I have taken one of the screenshots. The left part of the screen and the right part of the screen represent very similar data, except that the precision is different. So in first case, we are using a full precision value, FP32, while in the second case, we are using a half precision value, which is FP16. And in both the cases, we are trying to figure out how much VRAM uses will be there for a Minstrel 7B model. And you can see that Minstrel 7B with a full precision value is trying to utilize approx of 30 GB of data. Also in the bar graph there, it actually divide the VRAM utilization among different categories, right? You have CUDA kernel, then you have parameters, you have architecture, and then you have outputs. You can see the maximum allocations is actually for the parameters. While on the right side, you can see the model is actually using half precision value and you're just utilizing 16 GB. So what I want to highlight is even a 7 billion parameter model will require for its inference 16 GB of VRAM. When we are talking about LLM inference, there are many metrics which are allocated to it. For the performance, we will highlight two of the performance metrics. The first one being latency. Latency is related to how much time is consumed. And time consumed is always, time consumed for creating the response. So when you talk about the response, it can either be the time for the first token for the generation or time for per token output generation or the total generation time. The second metrics which we have here is about throughput, which is basically the number of requests or the number of token it can process. So both of these metrics plays a vital role, and when we are trying to optimize it, basically we are trying to fit in the best metrics. So while we are optimizing it, there are different ways. Of course, this session is all about quantization, and of course, all the following slides will only talk about quantization. What I want to say is, other than quantization, there are other methods also which we can use for optimization. Two of the major methods, such methods are knowledge distillation. When you talk about knowledge distillation, what we are doing is we are taking a huge LLM teacher model, and using that we are trying to train a LLM student model, smaller model. And then when you create a distilled or a smaller version of the same LLM model, then the smaller distilled version is further used for the prediction or any kind of generation. The second method here is about LLM pruning. As the name suggests, pruning is basically removing your connection on weights. You can do it in two ways. You can do a symmetric pruning where you remove the weights in symmetry, while you can also go asymmetric pruning. In either case, you will actually remove weight, and therefore from a large LLM model, you will turn out to have a smaller pruned LLM model, which can be further used for generation. So with that, coming back to the agenda, we have talked about why do we need quantification and how do we represent these numbers internally. Now we will start with the major topic, which is what is quantification. So as the name suggests, quantification is basically to store the model parameter from a higher precision to a lower precision data. And the graph here shows that you have a data which has been spread across higher granularity, and it has multiple data points. You're trying to squeeze it into a lower precision value, and that's why it fall flat. The quantized weight fall flat, and it is represented in a lower granularity. While we are doing it, the granularity can be measured per tensor, per channel, per group. What does it mean is, anytime when you are representing a vector, vector is basically a matrix representation. So if you are trying to do the quantization across the whole vector, then it is per tensor. While if you're trying to quantize only the channels, which is the axis, then you can quantize along the x-axis or the y-axis. You can also quantize per group. Per group means only selected groups of elements which you can choose and you can quantize. Two of the major aspects of this are also scale and a 0 point. So we understand that we are trying to fit in a large range of values from higher precision to a lower precision. Therefore, we have a range from R min to R max, which we are trying to fit now into Q min to Q max. And this is a very linear mapping which can be shown by the formula there, which shows a linear equation where R has been represented as a function of Q, and where come up two major factors, which is S and the Z. S here is called the scale, and S is nothing but it is the difference between the max and min of the higher precision value divided by max and min of the lower precision values. And then we have the 0 point. 0 point is actually the value in the lower granularity or lower precision data representation where the zero of the actual value has been represented. We will see scale and zero in much detail in upcoming slides. So what are we trying to quantize? We saw that we are trying to quantize the weights or the activation. In the table below, you can see if you're trying to quantize both weight and activation, you can write it as W8, A8. Means you're trying to quantize both. But because quantization itself is related to cost, there are very few hardware which are available which can help us to quantize both weight and activation. While in most of the existing the techniques which we are using now and we will discuss, we have mainly the quantization of weight. So we have W8, while activation is used as is, and therefore A32 means 32 representation of the activation. We also have quantization symmetric and asymmetric. What do we mean by symmetric and asymmetric quantification? When we have symmetric quantification, you can see we have a vector at the top and the highest value there is 10.8. If you do the symmetric quantification, then you actually take the range from the highest value to the negative value. So it is 10.8 to minus 10.8 to 10.8 in order to create a symmetry. And then you try to map it to a lower precision value. Therefore, a 0 from FP32 representation is always represented as 0 on int 8. And you will always have a symmetry across 0. Therefore, it's kind of symmetric distribution across the 0 on both the representation, higher granularity as well as a lower granularity. But if you take a asymmetric distribution, it is not a symmetric distribution, and therefore the range is basically taken as the lowest value in your vector to the highest value in the vector. The lowest value highlighted in green is minus 7.59 and the highest value being 10.8, and you are now trying to squeeze it into a smaller dimension, smaller data type in a min and max, and you can see because it's asymmetric, the 0 is no more mapped to the 0 now, and 0 is mapped to some other value, and the value at which the 0 of the actual distribution is mapped to a lower precision value is called a 0 point. So just to give an example of asymmetric quantification, if you see the blue line at the top, right, you will have a vector and you have two values, alpha and beta, which represent the highest value and the lowest value. When you quantify, because this is a asymmetric quantification, you get different values. Of course, we're not going into details of each of the formulas, but just to highlight, because this is an asymmetric quantification, the 0 of the blue line is mapped to 130 in the orange line, and 130 is actually your 0 point. And when you dequantize it back, when you dequantize it back, you will see that the values will come as is, as we have before quantification. But what I want to highlight is the value is not exactly the same. And what it means is every time when you do this packing, unpacking, or quantification, dequantification, there will always be a lack of accuracy, and we have to bear up with it. There is one more term which is called clipping. Quickly going through clipping, if you have a vector like this, which is represented, where most of the value, if you see, are ranging close to zero, right? Close to either negative or positive, close to zero. But we also have certain outlier in the vector, which is 256, too huge, right? If you have outliers into the value, then it will create a drift. If you have too much outlier, then most of the values are in a range, but certain outlier will create a drift. And in order to reduce this error of outlier creating a drift, we actually clip the values. So we'll take clipping. Suppose in this example we have taken the clipping values from -5 to 5, and therefore each value which is outside the clipping will always be mapped to the maximum value. This is a good, this is a good example. Clipping will always help you in order to reduce the drift. But what happens is when you dequantify it, right, you will not be able to recreate these outlier values, and therefore there will be loss of accuracy. Some of the common techniques of quantification, two of them majorly. One is the post training quantification, which always happen post the training happened. Okay, and it happens for both weight and activation. When you are taking it, you can do it either symmetrical way or asymmetrical way. If it go by the example, GPTQ, which is the best example of, in fact, Hugging Face has introduced two common ways of doing the post training quantification. One is GPTQ and other one is GGUF. Talking about GPTQ, it is a great quantification method which is used in order, which actually runs on full LLM on a GPU, and it is a post-training quantification method which help the model smaller with the calibration data set. The idea behind GPTQ is very simple. It quantifies each weight by finding a compressed version of that weight that will yield to a minimum mean squared error. The second method here is about quantification along with the training. And when you're doing quantification along with the training, it will be more accurate, better performance. But of course, there is a huge cost associated with it because you are trying to do each step. Like we talked about calibration, range estimation, clipping, rounding, everything will be done along with the training process. And therefore, it is a expensive computation of doing it with the training. And the example of this is QLoRa. LoRa is a PEFT model and it is a fine-tuning model which has been developed. And if you quantify the LoRa, we have a QLoRa model, and this is a perfect example of QT, which is basically quantification along with the training. Talking about some of the challenges, we figured out that there is always a loss of accuracy because when you try to dequantify, you are never able to recreate the same values. Therefore, there will always and always be a loss of accuracy. Second thing is about the emergent features. What we mean by emergent features is new, many new models, LLM models are coming up, right? With the open source LLM or OPT, which is the Open Pre-trained Transformer, which has been launched by Facebook in 2022. And with each of these models, there are many emergent features which are coming at scale. Now, these emergent features are actually the outliers in which the classical linear quantification, which you talked about, will actually fail. And then we have to work with this resolving these outlier features. And there are many papers which has been published in order to handle these outliers. Third one is about the smooth quantification. This is a peculiar challenge which happens when you are trying to apply W8 A8, basically when you are trying to quantify both weight and activation together. And then we saw that huge amount of time which is associated with quantification. You can see that it's smallest in the picture below. The smallest model which is being quantified using GPTQ is 1.7 billion parameters, and it still takes 3 minutes to quantify. Also, we have limited hardware support, which we saw with the quantification process. Now, finally, the decision is about whether we should choose a quantified large model or a smaller non-quantified model. And the researchers shows that it is always advantageous to use a quantified model rather than a smaller non-quantified model because it has reduced latency and enhanced throughput. With that in picture, we come to the end of this session. I thank you so much for being patient with us, and I hope we are able to together explore some bit of quantification. Thank you.